Hello everyone, welcome to the final lecture for this week, week 5 of the Introduction to Data Science module. We'll be carrying on with the machine learning topics. Today we'll be introducing linear regression. So, as Zach outlined in the Introduction to Machine Learning lecture, the basic scheme for any supervised machine learning problem is, let's see here. We have some features, x. These are measurements that we expect to have always for any data point. And we have some labels, y. And we would like to be able to predict the label y given a set of features x. So we're looking for some mapping from the features x to the label y. In other words, there is some kind of mapping or function f that will accept some features x and approximate the correct label y. Our job, or our task in machine learning, supervised machine learning, is to develop a model, f, that makes this approximation of f of x as close to y as possible. And the most basic form of machine learning under this kind of framework is linear regression. Now we start with linear regression for a few reasons. The first reason is hopefully many of you are already familiar with linear regression. So it will not be that new to you conceptually, but we can use it as a launch pad for talking about all the kinds of things we think about in machine learning more broadly. So this brings us to the second reason we begin with linear regression, is because many times when we're trying to improve a machine learning model or set up a machine learning problem or task, we'll be thinking about certain concerns or ideas to guide us. But it won't always be obvious exactly how these ideas might apply to any given task or any given problem. And we can often use linear regression as a baseline kind of approach to orient our thinking with respect to more complex problems. And we'll see that again and again as we dive into the complexities of machine learning. We return to linear regression as a kind of foundation for explaining more complex ideas. So, linear regression, in its simplest form, is you are trying to find a linear relationship between two variables, y and x. And since this is a linear relation, the form of the kind of equation must be x times some number plus some other number. The x is our feature, y is our label, and as soon as we say there is a linear relationship between them, that means there can only be essentially a constant plus some multiplier against x. It's the equation of a line. So if we have some measurements, x, y pairs, where we know what the label is for particular observations, particular data points, then we can calculate what the model parameters beta naught and beta 1 ought to be. To do that, we have to define what we mean by making this approximation as good as possible. Or, what the best fit, what the line of best fit, how is that defined? And this gets into the idea of metrics, which we'll talk about in subsequent lectures. In the case of linear regression, what we mean when we say we're going to fit the line to be as close to y as possible, it means we're going to try and minimize the sum of the square distances between y, the individual y's, and their corresponding points on the line of best fit. This is known as the sum of squared errors, or equivalently, the mean squared error. The mean squared error is just the sum of the squared errors divided by the number of data points. So these two are mathematically, functionally the same for the purposes of this discussion. So, this guides us to a calculation of these model parameters. And once we have these model parameters, beta naught and beta 1, in the future, if we were to only measure x, because perhaps that's all we can measure, we could predict y. So for example, I might have an engine, and I would like to predict how much fuel the engine will consume when it's operating at different RPMs. It's easy for me to measure the RPMs at any time. Most vehicles, whether they be a motorcycle or a car, vehicles running with engines have a what's it called? Is it a tachymeter? No, that's the name for a watch. I've forgotten the name of the device. But they have a gauge, right? A readout of how fast the engine is running. But often they don't have a gauge for how much fuel you're consuming. That might be something we can only accurately measure in a lab. So in the lab, I measure the RPMs, and I also measure the fuel consumption. And then I fit my model, since I have the fuel consumption at different RPMs. And now, in principle, I could perhaps predict the fuel consumption at any RPM just by measuring the RPM and plugging it into my model. Now, fuel consumption as a function of RPMs of an engine is surely not linear. So we might want a different kind of model for that scenario. But it at least illustrates the goal. The example illustrates kind of the goal here. So let's work through some examples. We actually have, speaking of fuel consumption, a data set about motor vehicles. So these, if I remember correctly, rows correspond with different locations in some country. I don't remember which. And each location has a different fuel tax. There's a different average income there, different amount of kilometers of highway, the average number of drivers there are per person in the area, and the gas consumption in perhaps like a month or a year in that area. I don't remember what the units of these things are, but we could imagine wanting to predict how much gas would be consumed in a given region based on these factors. If we found that taxes lowered fuel consumption and we wanted to discourage driving in our area, perhaps to reduce pollution, then maybe we could raise the tax. Or if we find that building more highways leads people to consume less gas because they're able to travel more directly, perhaps we could build more highways. Or maybe more highways leads people to consume more gas because now they start driving to places that previously they could not reach easily by car. So we might be interested in trying to predict how much gas a region might consume as we make different policy decisions that could influence some of these factors. At the moment, we'll plot one of these variables against the gas consumption. So we're going to treat the gas column as y, and then we'll consider another column as x. So we can see that the percent of the population driving appears to be roughly linearly correlated with the gas consumption in that area. As I could draw a line through this cloud of points, and that would more or less describe the overall trend in the data. So we can imagine drawing some lines through this cloud of points. We have two here, this green line and the red line. And then we would ask ourselves which line describes the data best. And in order to decide between these two lines, as I mentioned earlier, we need to define a metric for how well they describe the data. And this is very generic in machine learning. We'll talk more about metrics probably in the next lecture. But the metric is a gauge of kind of the thing we value in our machine learning model. So what we value about our trend line is that it should make predictions, that is, the value given at a particular point on the line, should be as close as possible to the actual data points themselves. So we would be interested in looking at the difference between data points and the fit line, whether that be red or green or some other fit line. So recognizing that as what we value, we can write down the error, which is the y value, the label we're trying to predict, the gas consumed, minus the prediction of the fit line. So we have here that formula for the fit line. Now, we want to make we're not just concerned about, a single error, like the distance between this point and the line. Hold on just a moment. Okay, sorry, I was getting a phone call. We're not just interested in one data point, but we're interested in the errors between the fit line and all the data points. And we want to simultaneously minimize the error between the fit line and all the data points. So we want to somehow calculate kind of the total error. But some of these errors will be positive because the value will be greater than the fit line, and some of them will be negative. And in general, the positive errors and the negative errors might tend to cancel out. And really what we want to minimize is not, we don't want to minimize the total error. We want to minimize the distance that any given point is from the line. I don't care whether the point is above or below. I just want to minimize the distances. So what we do is, instead of considering the error, we consider the squared error, which will give not positive and negative errors, but squared errors will always be positive. And so if we add up the squared errors, we'll get some kind of quantity that represents the total error, the distance, the total of the distances between the point and the lines. Now, it won't be exactly that, but it will be a good proxy. Now, you might object, why don't we just take the absolute value if we want the total distance, the total errors? And we could do that, but it turns out that we get quite nice mathematical properties when we choose a metric of the mean squared error rather than the mean absolute error. And it's because of these nice mathematical properties coming from squaring the error instead of taking the absolute value that we choose this metric. I'll loop back around towards the end of the lecture and describe what those properties are. So if we were to expand out this mean squared error, by expanding the squared error terms, which is what I am doing right now. So here I've written out the formula for EI, and we see that the mean squared error depends on our model parameters, beta naught, or beta 0, and beta 1. So what we will do to decide between different fit lines is consider which fit line, which beta naught and beta 1, which correspond with different lines, minimize this mean squared error. We want to minimize kind of this total error between the points and the lines. Often in machine learning, when we want to minimize some quantity that is a function of our model parameters, we will call that quantity the cost function or the loss function. So we want to minimize the cost or minimize the loss in many machine learning tasks. In the future, when we consider other machine learning tasks and consider different metrics, we will sometimes call them objective functions or utility functions, things we want to maximize. So we want to maximize utility or the objective, but we want to minimize loss or cost. This is just some jargon that you might run into in the world of machine learning, so I thought that I would highlight it here. So, in the case of linear regression, there is actually an analytical solution for what values of beta naught and beta 1 minimize this mean squared error. And if you Google like ordinary least squares regression, there's a Wikipedia article on ordinary least squares, which, let's see, here we go, simple linear regression. So here it says we want to solve the minimization problem, minimum of q, that's what they're calling the mean squared error, which is y minus a minus b times xi quantity squared. That's what we have in our notebook. And using some calculus, it's possible to find the minimum here by taking a derivative and setting it equal to 0 and then solving for a and b, which are given here as alpha hat and beta hat. So it's possible to derive from this minimization problem exactly what the values of alpha, or what the model parameters should be. In our case, beta naught and beta 1. I'm not going to go through that derivation here. It's not terribly important. And in part, I think it's not all that interesting because usually in machine learning, there will not be such an analytical solution. It will generally not be possible to find the absolute minimum of an analytical solution for the absolute or global minimum of the mean squared error. We will usually need to do some kind of iterative process where we update beta naught and beta 1, or our model parameters, in order to try and recalculate the mean squared error and try to essentially guide ourselves to a minimum of mean squared error by following the direction in which mean squared error is decreasing. And we'll discuss this. This method is called gradient descent, and we'll discuss that later on in the course. But knowing that, our goal is to minimize the mean squared error is important, and that will show up time and time again in machine learning problems. So in scikit-learn, we can do this quite easily. We can import a linear regression estimator. We can initialize this estimator, so we construct a linear regression object. And in order to calculate the model parameters that will minimize the mean squared error, as with any estimator, we take our estimator and we just call its fit method against the data we want to fit it to. And then I'll go ahead and make our scatter plot, and I'll plot the lines we had before along with the line of best fit as calculated by scikit-learn. So you can see actually neither green nor red minimizes the mean squared error. In fact, this black line does it, which I probably would not have guessed by eye. And we can inspect what the model parameters are by looking at the attributes of our estimator object. So for every, say, 10% increase in the percent of population in the region that's driving, we would expend an extra 140.9 million gallons of gasoline per year in that region. This must also be per capita or something. There must be a scaling here by population size. Okay, so one thing I want to comment on is, well, okay, actually I'll hold that comment until later. So I mentioned, in general, it's not going to be possible to use this analytic solution to find the best model parameters for minimizing the mean squared error. And there's a number of reasons that won't always be possible. Sometimes no such analytic solution exists, and other times, even though the analytic solution does exist, it might not be practical to compute what these values actually are. And so one generic way of minimizing the mean squared error, or whatever the cost or loss function might be, as a function of the model parameters, is gradient descent. So what do I mean by gradient descent? Let's consider the mean squared error as a function of the model parameter beta 1. So we'll actually make a plot of what the cost function would be with respect to beta 1. I'm going to hold, meanwhile, beta 0 fixed at the value of the intercept that came out of our best fit model. And I'll let beta 1 vary from 1300 up to 1500. And I calculate the mean squared error for each value of beta 1 that I might consider. So when I hold beta not fixed, what I'm doing is I'm holding the y-intercept fixed, and then I'm letting the slope vary up and down. So you can imagine this black line tilting up and tilting down, but holding the y-intercept, somewhere over here, fixed. And when I let it dip down, many of the points are going to move above the line and far away from the line, and the mean squared error will probably go up. And as I tilt it up, many of the points will end up under the line, and their mean squared error will increase and increase. So as I move the line up or down, the mean squared error will tend to increase. And in fact, it increases like this as I vary beta 1, as I vary that slope. So this actually is a parabola. And we could see that we should have expected that from the formula here, in fact. We have the sum of a bunch of squared terms, and so it's not surprising we end up with a parabola in the end. Now, what gradient descent means is, let us imagine for a moment we had made some guess of what our model parameter should be. We guessed beta naught to be this value, and we guessed beta 1 to maybe be 1350. So we were here.
Now, how should we minimize the mean squared error? Well, if I could take the slope of the mean squared error as I vary beta 1, I would just want to go downhill. So I could follow the slope downhill until the slope hits 0, at which point I know I'm at the bottom of this valley. And that's exactly how minimization works in calculus, in an analytical sense. And all gradient descent is about is following the slope iteratively, taking steps downhill until I can't go downhill anymore. So I just calculate the slope. That tells me the direction to go in. I take some step. I calculate the slope again. Take some step. Calculate the slope again. Take some step. Calculate the slope again. Slope again. Take some step. And my step should be proportional to the severity of the slope, so that when I get to the bottom and the slope becomes very shallow, I start taking very little steps, so I don't overshoot the minimum. And when I get to the minimum, I stop. If, on the other hand, I take a very large step, then it's possible I end up clear on the other side of the valley. And I could just bounce back and forth across the valley. And if my step is large enough, I'll even start to walk up the valley instead of down. But if I take small steps, then simply walking downhill should eventually bring me to the bottom. So this iterative method of continuously stepping downhill is what gradient descent is. One example of where gradient descent is used is what's called a Huber regressor. So the Huber regressor is a linear model, but it minimizes a more complicated loss function. And it's not possible to calculate what the model parameters, in this case these W, ought to be in order to minimize this loss. And so the Huber regressor, since we can't calculate analytically what these weights should be, the Huber regressor uses gradient descent to attempt to minimize this loss. And in fact, let's see here, Huber regressor. So the Huber regressor has this max iter value, or keyword argument, that sets how many iterations of gradient descent will be taken. So this time we make a Huber regressor object here. And once again, we simply fit that to the data we have. So we're trying to find the best fit line for predicting the gas consumption based on the percentage of drivers. And we can see the Huber regression line is different than the simple linear regression line. these give two different predictions. And that makes sense because the Huber regressor minimizes a totally different loss from the simple linear regression loss. So choosing a different metric to optimize will often lead to a different model. And sometimes will even necessitate an entirely different optimization approach. The simple linear regression model we can optimize analytically. We know what the answer is in advance. Huber regression, we have to use gradient descent. But scikit-learn does that for us. Nowhere did we have to write anything about gradient descent or know anything about gradient descent. Scikit-learn handles that internally in the Huber regressor's fit method. Now, of course, it's still useful to know about gradient descent. There are times when you explicitly have to handle gradient descent. They won't come up in this course, but it's a very important concept within machine learning, and it underlies many models, and so it's useful to be aware of what these models are doing for when you might need to solve problems with them. So, this whole time with this example, we've been working with just one variable from the data set, percent of population driving. But it's in general very difficult for a municipality, some city, or a region to control the percent of the population that drives. Some things that it can control are the amount of miles of highway. Often because, the government is the institution building the highways, so the government gets to decide. And the government also sets the taxes. And in this way, the government might be able to influence how much gas is consumed. So we might not be interested only in this variable, but how all four of these variables contribute to how much gas is consumed. And so we might want to simultaneously calculate a linear regression against all four of these variables. Which brings us to the topic of multivariate regression. So before we attempt a multivariate regression, or talk about what that might mean, we should first of all consider the relationships between the variables in our data set. Before we began with any of this linear regression, I plotted a scatter plot of the percent of the population driving against how much gas is consumed. And we saw that this is a roughly linear relationship. There was a cloud of points with some spread to it, but they trended, kind of along a line. There's nothing, it doesn't look like they follow some kind of more complex curve. They're not rising and then falling. They just linearly increase. So before we try to do linear regression on the other variables, we should check whether or not they even have a linear relationship with the gas consumed. So, for example, miles of paved highway, it's not very clear. It appears like it at first maybe increases the level of gas consumed and then decreases. But even that, it's somewhat hard to say. There's a lot of scatter. The points are kind of spread out. And it's hard to really say what the trend is at all here. If we look at average income, wait, where did tax go? Let's add tax in here. I'm not sure why it's not there. I'll put this as gas tax. If we look at the gas tax, I would say, as gasoline taxes increase, the amount of gasoline consumed seems to decrease, as we might expect. But again, it's not really clear that this is a linear relationship. It does appear like maybe this is somewhat curved. It's just not easy to say whether this is linear or not. And if we look at the average income, we find maybe some negative correlation. This looks like it could be linearly related, and it looks like the gas consumption is trending downwards somewhat as income increases. But again, it's not totally clear. The percent of population driving is by far the most clear linear relationship we have. So it might not be very wise to fit a linear model to all of these features, because not all of them appear to have a linear relationship with the gasoline that's consumed. Nonetheless, we're going to do exactly that. We are going to fit a linear model to these different features, because at this point there's not much else we are able to do in our toolkit of models. And furthermore, pedagogically speaking, I want to teach you about multivariate regression. So now, since we don't have just one explanatory variable, one x, we have several different x's. The tax, the miles of paved highway, average income. So we'll need a somewhat more complicated formula for our model. We don't just have x. We have x1, x2, x3, and x4. And those will be the 4 different explanatory variables we're considering. And accordingly, we have a slope for each of our explanatory variables. And this is no longer the equation for a line, but the equation of a plane, a flat planar surface. And in 2D, this is, truly like a plane, like the surface of a table. But in 3D or 4D, it's what we call a hyperplane, which is we can't even imagine a 3D hyperplane, because to do so we would have to think in 4 dimensions. Just like to think of a 2D plane, we think in 3 dimensions. So unfortunately I can't describe to you what this looks like, but it's a generalization of the plane, just like a plane is a generalization of a line. In any case, it's a linear model of 4 different variables. Y is a linear function of 4 different variables. And we can write this very generally as y equals the sum over some j, that's the number of features we have here, of beta j, the different slopes or model parameters, times xij, where xij is a matrix where I indexes the different observations, the different data points, these dots, and J indexes the different features, the different explanatory variables. So here we have J running from 0 on to 4, and we have left I as I to represent the different data points. So I use the word observation, meaning different data points, and features, meaning different explanatory variables. So I labels the observations, J labels the features. And this matrix we call the feature matrix. So a feature matrix is essentially this table, except without the gas column, because the gas column are the labels we're trying to predict. So this is our feature matrix. Each column corresponds with a different feature. Each row corresponds with a different observation, a different data point. And time and time again, we will be talking about feature matrices in the context of machine learning tasks. And we can try and visualize, at least in 3 dimensions, 2 of these variables together, 2 of these features together. So we have on this axis the gasoline tax, on this axis the percent of the population that's driving, and then on this axis we have the gas consumption. And I realize this is maybe not so easy to see or understand. Let's see here, come on. I really can't change the figure size here? Oh. I want to do it here. There we go. I realize this is maybe not so clear. It's not easy to represent 3 dimensions on a flat screen. No surprises there. And unfortunately, it's furthermore not easy to make this interactive so that I could rotate it around. But as we anyway add more and more features, we can no longer visualize the spread of the data at all. But the idea is when we want to fit a linear model to these points, if we were using just 2 features, we would be fitting a plane to these data points. So a plane would be slicing through this cloud. And the height of the plane at any given x1, x2 coordinate, so at any point on this grid at the bottom, we would go up to the height of the plane, and that would be our prediction for the gas consumption. So we'll actually perform that fit on tax and drivers, the 2 elements we're plotting here, the 2 features we're plotting here, and attempt to visualize that plane. So there's the plane. We can see that if we look at the edges, as the tax increases, the amount of gas consumed slightly decreases, and as the number of drivers in a region increases, the gas consumption steeply increases. So this plane slices through the space, decreasing along the tax axis and increasing along the driver's axis. And again, in higher dimensions with more features, we couldn't visualize this at all, but in principle, it works the exact same. I'm just trying to show some geometrical intuition beyond one dimension. Another way of visualizing this is to look at the fit line for drivers versus gasoline consumed at different values of the tax. So I mentioned if you look at this edge, you can see that the gasoline consumption increases as the percentage of population that drives increases. But this slope changes as I move along the tax axis. And so, I apologize. If we were to slice along some line through the tax axis, we would get a cross-section of the plane and the points. Now, the distance from the points from our cross-section is represented by how intense they are. So, for the dark points have a tax rate close to 5, while the further away points have a tax rate closer to 9. As I change the tax value, some points become darker. These darker points have a tax rate closer to 8%. And I can go all the way up to 10. And these lighter ones were the ones that were dark. So if you, for instance, look closely at this one, that's a point that has a tax rate of 5 or 6%. While this point is one that has a tax rate much closer to 11%, to the point where when I got down to 5, it actually totally disappeared. So when I got to 8, a point appeared here. And as we look through these cross sections, we see the slope and maybe not the intercept, but we see the line changing as we look through different cross sections of that plane. So hopefully this gives you some amount of intuition for what's going on in multivariate regression. We have predictions that we make by multiplying a vector of model parameters against our feature matrix. And we try and calculate which model parameters, beta j, minimize the mean squared error of these predictions relative to the labels. And to actually calculate these beta j, in general, if I go back to ordinary least squares regression, the general case is the vector of model parameters is calculated based on the feature matrix and the vector of y values. And you can see there's a matrix inversion here. So I have some matrix multiplication with an inversion. And matrix inversion computationally is quite expensive and sometimes does not work so well. So for general data sets, especially large data sets, inverting the feature matrix might not be feasible. Which is one of the cases I mentioned earlier for gradient descent is even when the analytic solution is known. So the analytic solution is known. It may not be practical to calculate in this case, because sometimes it's not easy to invert this product of the feature matrix with its transpose. So when it's not possible or easy to calculate that matrix inversion, even though we know the analytical solution, we might still use this gradient descent method, because the iterative gradient descent method is relatively cheap and easy to implement. So that concludes our discussion of linear regression. As I mentioned, in the lectures next week, we're going to be moving on to metrics and beyond, and we will keep next week we'll probably cover metrics and model selection, and as I mentioned, we'll keep revisiting this idea of linear regression over and over to get our bearings on concepts of machine learning as they become more and more complex. Thanks for listening.